able to give a talk or live or hopefully.
Apologies to disappoint everyone. I had to change the title of my talk primarily because I'm still processing the results of my previous one. So I had to limit it to a slightly different talk for today. And today I kind of wanted to focus more on one of my projects which stimulated from the kinetic limitations of the floating catalyst CVD process for carbon nanotube formation. So a little bit of background in terms of understanding why we want to make carbon nanotubes and why we want to make them on a mass scale, other than, it's a cool material to make, is that we have quite a lot of problems with methane emissions that are already coming into the atmosphere from fugitive emissions on landfill sites and farming. And this problem, of course, is exacerbated even more with the polar ice caps melting, and the Arctic circles retreating as more and more methane gets exposed as emissions into our atmosphere. And of course, as you all well know on this phone call, that methane has a much higher global warming potential than carbon dioxide. So this could really cause a completely catastrophic event on our planet's global warming. So our current treatments with natural gas and methane is really just taking it and burning it and oxidizing it into around about 50 gigajoules of energy per ton of methane, but also producing quite a lot of waste product. So that carbon really is locked up as a waste gas that really we can't really do much with it. And so one way to actually deal with this in a more efficient process would actually be to pyrolyze that methane or reform it into forming hydrogen as your source of energy and some solid carbon. Now, the caveat with that is that forming that hydrogen as an energy is actually less, you're actually producing less energy per ton of methane than you would do if you're oxidizing in the process. And so that carbon, that solid carbon, must not only have societal benefit, but also some form of economical benefit to be actually used at an industrial scale. And so one of the more attractive ways of forming that solid carbon is turning into carbon nanotubes. There are other methods such as forming carbon black and carbon fiber, but carbon nanotubes really has started to show its properties can outperform those other allotropes of carbon. So the one way to make carbon nanotubes on a mass scale is known as the floating catalyst CVD process, in which we take natural gas as our methane or methane as our CNT precursor, and we also put that in alongside with catalyst precursors such as iron and a promoter precursor such as sulfur. And within this furnace, is what's not shown is that there is a natural temperature profile that always exists in these furnaces, and you get an initial decomposition of your iron and sulfur, forming an initial part of your catalyst at this point in time. And in reality, actually, this occurs, and then at the hot point, your catalyst particles evaporate back into the gas phase. And what was actually found from both academic and industrial studies was that most of your carbon nanotube formations happens actually in this downstream region of the reactor. So this is really where your catalyst particles are reforming, and a lot of that natural gas that you've put in has now formed an active species on which, from which carbon nanotubes can form. And what's nice about the floating catalyst process is that you can actually retrieve a macroscopic material that has been formed from a self-assembled carbon nanotube formation, in which individual carbon nanotubes that are formed on the catalyst particles bundle together, forming bundles, and those bundles then collide together, forming a self-assembled structure that's anisotropic, which can be retrieved in either a matte or fiber form, depending on how you want to process the material. And so really, for this to be kind of an industry relevant process, what you want to maximize is your production area and maximize as a result your carbon nanotube formation and hydrogen as your energy fuel from this. So what we really want to explore is how can we actually begin to actually extrapolate and densify this reaction zone that we're able to form. Now, of course, the question is also borne out in terms of how much methane can you actually reform using this process? And this is really what this project kind of tries to address. So it's kind of natural to assume that if you put in more catalyst, you can end up putting in more of your carbon reagent and form more carbon nanotubes and therefore process more of your methane through to forming hydrogen gas. But of course, in reality, there will probably inevitably exist some limit. And academia doesn't really address these limits because it's more to do with industrial processing and industrial kind of limits. But it's quite an interesting phenomenon in terms of, from an aerosol's perspective, is there actually a point in time which you can't make any more carbon nanotubes and the process will stop to exist? So what we tried to do here is to develop some physical and chemical models that can back onto each other in order to explore and extrapolate these boundaries. So we developed, kind of came up with 3 of the most common collisions that you would see in the floating catalyst process, which is your active species collisions forming your CNTs, your particle growth through coagulation, and your polyaromatic hydrocarbon forming collisions, which is your competitive pathway to your CNT forming, because when those polyaromatic hydrocarbons are actually precursors to soot formations, which is an undesirable product in our reaction. And we made this the physical model slightly more simple in terms of the fact that we use analytical solutions to these coagulation problems and these collisions for the rates in order to understand this, mainly due to the fact that there's not actually a lot of experimental evidence that we can back onto using more complicated models. We used, in order to calculate the concentration of our species as a function of reactor axis, we used methane pyrolysis and methane oxidative literature that has been studied before for soot formation. So the chemistry for the C1 to C4 forming carbon molecules within your reactor is really what we're using for these chemical formation mechanisms. So one of the first things that we did in this was to actually measure the constant species distribution as a function of reactor axis. And the way we were doing this was we were extrapolating FTIR measurements from our hot furnace and just taking measurements at each and every point of the furnace axis. And what we found was that, even though this is not actually confirmed, that what is predicted from the literature as being the most active species for carbon nanotube formation, which is acetylene, we found that one actually is really well modeled by these oxidating mechanisms that are out there in the literature. And so, as you can see, the blue line, it's not only actually the distribution along the reactor axis, but also the order of magnitude that can be both well modeled and is also shown experimentally. Now, of course, there are some caveats to this in terms of if you look at other molecules such as ethylene, you're actually not able to see the same kind of trends. You're able to see a distribution trend that can almost mimic it, but of course some tweaking is required, and this of course is inevitable because the oxidative models are studied in an oxidating environment, and we work predominantly in we work solely in a reducing environment. So if you were to take all those collisions that I've just described and map them out as a function of your catalyst mass versus your carbon input, and specifically focus on that region in which you are producing the most amount of carbon nanotubes, you get a competition pathway that is set up. And as a result, your synthesis region, which is where you're producing the most amount of your carbon nanotubes, and this is from a physical perspective, where your collisions between your acetylene molecules and your particles are dominant. This is bounded by 3 distinct regions. The iron-rich region is in which where your particle-particle collisions are on the same order of magnitude and in direct competition with your acetylene colliding with your catalyst particle. And this can be explained quite simply as where you're putting in far too much mass at that distinctive point in time, and your particles are you'll be running quite a dilute synthesis process relative to the carbon. The carbon-rich zone is probably the most, the easiest one to explain experimentally, as you just, without enough catalyst being within that process, you end up forming soot. Soot, of course, being the undesirable product, as I've mentioned, and that's logically quite one that it can easily be shown experimentally when you hit that boundary condition. But really what I wanted to talk to you about is actually this particle coarsening zone. So this particle coarsening zone actually constitutes to an upper kinetic limit for the coagulation of your aerosols. So what we see here is that, you know, endlessly you could put in more and more iron, beyond which you can put more and more carbon. But actually, in the way that carbon nanotubes form, the mechanism by which they form, the predominant thesis for that mechanism, results in there actually being a diameter-dependent limit for our CNT formation. And now, if you take that and you realize actually, okay, well, I can only put in a specific amount of mass into my synthesis process, and then after that, your catalyst will grow far too big and then inactivate itself, and you're unable to form the carbon nanotube particles. So really, this kind of graph kind of describes to you what would happen if you endlessly push that boundary. You would find that you actually start to hit that upper limit and effectively render your catalyst useless, and it will crash out into your product, meaning that there is actually a specific amount of methane that you are able to process with this floating catalyst CVD synthesis. So in conclusion, this work is kind of shown from a theoretical and physical standpoint that yes, there does exist a specific upper limit to the synthesis of carbon nanotubes, and that we can use these current models for oxidative environments to predict the formation of carbon nanotubes and show exactly where these kind of boundaries are. In terms of future work, what my team of experimentals, basically my team is able to do is to try and see where those specific size limits actually are. Colloquially, of course, it's all written up in the literature, but in reality, no one's really tried to specifically observe that as a study. What I'd really like to do is to extend these ChemChem models to carbon nanotube formation. And I think what we all in the carbon nanotube world certainly would like to know is actually what is that exact species that forms carbon nanotubes, and then also try and experimentally begin to map out those boundaries to better see how closely our model reacts with or how closely our model matches with what we see experimentally. And so finally, I'd just like to say thank you to everyone in my group for giving me a supporting hand in this, and especially a big thanks to all my sponsors, and a huge thank you to Adam. So thank you very much.
Thanks very much. Thanks, Michael. We have time for maybe one brief question. Anyone has any questions in the room or online? Whilst if you're presenting online, we have no way of constraining your time.
Oh, sorry about that.
I've got a question if no one has one.
Go ahead, Pete.
Okay, so I mean, the first slide that you showed about the motivation to do this is compelling, but I mean, the time to get this tech scaled up and cheap enough to make a difference is likely to be too slow and expensive, right? Because we've got to get these emissions down drastically within the next few years to make much of a difference. But so my question really is, in your heart of hearts, would it be a much better solution to reduce cattle emissions by just changing our diets?
That would address the farming issue, yes, but you'd still have landfill gas emissions. You'd still have vast quantities of natural gas as reserves at the moment, which can't be processed. And actually, in your point of how quickly can we scale up this technology, well, it is already being scaled up at the moment. So Huntsman Corporation, which is a very large engineering firm in the US, is producing over 5 megatons a year using this technology. And there is actually a critical mass of carbon nanotubes that you hit, which is around about 1 megaton, in which then you're starting to get the hydrogen production off it as an energy source. So in answer to your question, the scale up is already happening in terms of from that perspective. And yes, but although I don't disagree with you, I do think perhaps a dietary change and other mechanisms should be explored as well. So yeah.
Cool. Cheers, mate.
Okay, thanks, Michael. So we're moving on to our next slide.